So now we start officially the Enriched Finite Element Method course. In this course, we will look at the Generalized Finite Element Method, also known by many the Extended Finite Element Method, or XFEM. We will also cover other two methods, the Interface-enriched Generalized Finite Element Method and the Discontinuity-enriched Finite Element Method. The last two I've been working on heavily during the past 10 years or so. So the main idea, right, is that you could pretty much add any information that you know about your problem to get a better approximation, right, a better finite element approximation. And that could range from just a polynomial enrichment functions to functions that exhibit some strange behavior, like some sort of singularity, or like, for example, in crack problems, you can add a singular function to improve the behavior close to the crack tip, or you could add a function that has a steep gradient, right, that will help you find a better approximation for problems that have, for example, a very sharp heat gradient and things like this, right? So what we looked at in the advanced FEM class is that the Galerkin approximation is going to find in the space of functions that you're using the best solution for you, right? It's going to minimize the error while doing this projection. And the same happens here. We're still going to choose a Galerkin projection. It's just that now our space is going to be an enriched space. So we're going to have our standard finite element space, and we're going to enrich that with a space of functions, okay? That could represent pretty much anything you want. And so let's start with GFEM, or the Generalized Finite Element Method. So GFEM, you could argue that it started to be developed in the early 80s, right? The person who came up with this, well, there were a couple of groups who started working simultaneously on this method. The people behind it were Babuška and Melenc, right? And then in the Texas school, you had Armando Duarte and Oden, his advisor. And they basically started from what they were called back then the partition of unity methods, right? Partition of unity method, this idea that you have a framework that was called the partition of unity method that allow you to use, let's say, the shape functions of your background mesh and do something more interesting with that. Started the whole process, right? When that partition of unity was indeed the finite element discretization, the shape functions of that discretization, then the method became to be known as the Generalized Finite Element Method, okay? So it started with a high order approximation, so people started to use these to work with let's say an equivalent to p-FEM, but using enrichments, right? But then in the late 80s, the Northwestern school in Belitzko's group, right, they used an enrichment function that was discontinuous, right? They used the Heaviside enrichment function to represent a jump in the field, and they use also singular enrichments to a crack tip. And they could use the Generalized Finite Element Method to basically model fracture mechanics problems. These people called the method the Extended Finite Element Method, right? So basically, it is an application of GFEM to solve problems with discontinuities. This is what people today know as the Extended Finite Element Method, or XFEM. But they are indeed the same method, okay? GFEM, you could argue that it's a broader family of methods, because you can only, you don't have to only choose enrichment functions for discontinuities, but you can pretty much use anything you want, right? As we discussed. So before we get into the definition of the enriched space, we need some preliminaries, okay? So math is not going to get so messed up as in advanced FEM. So bear with me a few minutes, and then we start with what is the generalized finite element space. So as I said, this is also known as the extended finite element method. Okay. So we're going to talk about what is an open cover. Some terminology that is important in the beginning to understand what we're discussing. So that is basically just the definition of what an open cover is. So if you have our domain, if you remember, we call this domain omega, right? We want to make, in a way, a superposition of patches, right? And if you remember, we discussed what the cloud or support of a node was. Who remembers that from advanced FEM? What was the support of a node? What was the support of a node? So if I have, say we have a node here, the support that is the support of the node. So it's basically the elements that are connected to the node. And it's important because in finite element analysis, we know that the shake function that is associated to that node is equal to what at that location? 1. And then it goes to 0 where? At every other node, and consequently to every other edge of that support. Right? So let's call that x alpha is the node, and this is going to be our support of alpha, and we call that W. Yeah? And this is an interesting idea because if you think about that shape function, if we multiply that shape function with any function, what's going to happen to that function? Say you have a very interesting problem that has, during that, in the space of that support, it has very strange behavior, but you know a priori this behavior. So say there is really a steep gradient in the x direction, and you want to use that function. Now, if I multiply that function with this shake function associated with that node, what is going to happen? Who has a guess? Yeah.
It's still going to be 0 at edges or other nodes.
Yeah. So what is the effect of this multiplication? What is it doing?
Scaling.
Huh?
Scaling.
Yeah, it is scaling, but more importantly, it is what? What is it doing? If the function that I'm putting into the formulation is basically going to be non-zero in this cloud, right? Or in this support. Huh? Yes, it is localizing the function. Yeah, it is localizing the behavior that we want. And that is super cool, right? Why is super cool? Who can tell me what happens to the stiffness matrix? Yeah.
Because we can use it only where we have singularity and have normal
Yeah.
rest.
Yeah. that is pretty much the answer I wanted. So by localizing, you can say, well, I just want this behavior only here in the mesh, and that behavior is not going to propagate throughout the domain, right? And this has also important consequences in terms of solving, because how does our stiffness matrix remain?
Non-singular.
We will talk about that later, but it has nothing to do. Yeah, sparse. And this is very important. We like sparse systems. We can solve sparse systems faster, okay? And they take less memory, so we keep also sparsity. So you can already see that, this whole business of enriching is going to be tightly linked to our partition of unity, to our shake functions of our original mesh. Okay? So we talk about partition of unity, so let's define that more formally. So if you remember, if we have our shake functions phi sub alpha, and then of course alpha is the index set 1, 2, and goes to n being the number of nodes. And we have our phi sub alpha is a continuous function where the regularity, we call S the regularity of the solution, or the functions that we're using. So what this is saying, that is basically just that these shake functions phi sub alpha within the patch or the support or the cloud or the covering, basically all the elements where that function is non-zero has regularity S. And this is just saying that this is zero outside. Because of, and this is what we are, this is what it allows us to really localize the effect of anything we want in that support, right? The fact that it is zero outside. But the actual concept of partition of unity is that at any point in that domain, the sum of all of those enrichment functions, those shake functions, is equal to what? And this we saw it already in the other class. Yeah? That is why this is called a partition of unity. So if you take all those functions and you pick any point in your domain, this holds true. For the shake functions that we're using in standard FEM, you just take Lagrange elements, and you take linear elements, you take quadratic elements, cubic elements. This holds true for any point in the domain. So all of those are partitions of unity. Now we also look at PFEM. What happens with PFEM? Do we still have a partition of unity? No, we lose that property. That property is only held by the linear functions of PFEM, but the moment we add quadratic, cubic, and so forth, then we don't have a partition of unity anymore, right? Now, a partition of unity was very good for a few reasons. One of them was this idea of having the Kronecker delta property. Remember, who remembers what this was? Kronecker delta property.
It's 1 and at corresponding node and 0 in the other node.
Yeah, that was the answer. So basically the function is equal to 1 at the node, at the corresponding node, and it's 0 at every other node. That is called the Kronecker delta property. And this had a really nice effect, because we could associate the degree of freedom, right, to what? To the deformation, to the temperature. So the degree of freedom had a physical meaning. So when we're dealing with partition of unities, right, the degrees of freedom have a physical meaning. That's really important. That physical meaning is lost when we are losing this partition of unity, and therefore the degrees of freedom cannot be looked at isolated, right? We have to really evaluate the entire expression to get the temperature or the displacement field. Okay? So you are all with me so far, right? If you have any questions, please.
Well, one question with regard to the first definitions.
Yeah.
So in that little sketch,
Yeah.
The elements are called patches.
No, that's a patch.
The entirety is a patch. Okay.
Yeah. The whole thing is a patch.
And the cloud is
The same.
okay. Okay.
It's just it's different terminology that is used. These are called supports, patches, clouds, right? It's the same. Yeah. Now we're going to get into a very important concept now, which is why this works. We have the reproducing condition, and it's because of the partition of unity. So finite element reproducing conditions. So just to give an example, let's take linear shape functions in 2D. We have done that already, and well, you can really show that there exists some parameter. Let's call that parameter alpha, beta x. These are degrees of freedom, which is real, such that that symbol is interpreted such that beta x.
Excuse me, what is the first sign at the left?
There exists. Yeah. And this one here is such that. You can also write it such that, but you know. And also, we're going to explain what I'm writing here mathematically in a minute. There also exist some coefficients or degrees of freedom, a, beta, y, that are scalars such that these two are called reproducing conditions. In the case of a linear polynomial. So that basically means all the things that I just wrote basically means that you can find coefficients or degrees of freedom that can yield back in your approximation of your standard finite element approximation the linear polynomial, a linear polynomial, right? In the x and in y. And it's super straightforward to do that for linear polynomials because, you know, the a beta x is just the x value at the node. And the same thing with a beta y is the y value at that location, at the location of the node. Yeah, so here x, y is the coordinate. Of node xp. So what does all of this mean? If you are using a standard finite element, linear finite element method, right? We know already, right, that if we're using linear finite elements, we should be able to reproduce linear behavior, right? So all of this stuff that I just wrote is just to be able to reproduce x and y. That's it. Yeah, it's just more mathematically a bit more formal So basically, you can find coefficients that can reproduce or yield back that linear function in x and in y. That's all it says. A bit more mathematical, but that's pretty much what it says. Nothing more special. Yeah, so this is basically what we need to define before we start really getting into the part of the finite element spaces, right? So let's talk about spaces. In h-FEM, right? If you remember, we defined our space, let's call it SH, and this is a space of functions UH, such that UH is equal, and we know how to write that. We have phi alpha U alpha. So U alpha is a degree of freedom, phi alpha is the enrichment function, and then of course alpha goes from 1 to n, and here we're going to just say, well, it belongs to some sort of index set IH, which is the index set of nodes of the mesh. That's the same way to state that. But this is a space, so we do not fix the values of the degrees of freedom, and we say, okay, all of these are just scalar values. This is the formal way to define a finite element space. So we're saying that space is defined by functions UH, such that that function is written, the standard finite element approximation, right? And because it is a space, right, those degrees of freedom U alpha could be anything. They are just scalars. Okay, so this is basically defining the whole set of functions that we can use, because the degrees of freedom are not fixed. Yeah. So let's just complete here. You all know already these are the degrees of freedom, and these are our shape functions. Yeah. This is our standard finite element space. But as you would expect, this is not going to take us very far for some problems. So if we now recall the p-FEM version, let's call this SP, right? And it's very similar to this one. What was the difference? Who can tell me? Who can tell me what is the difference?
The nonlinear shape function.
Yeah, that is the only difference. So let's write this in a nice way. We're going to say, well, let's keep the same notation to specify the linear component, right? So this for me is going to be the standard linear FEM. And then let's add something that is non-linear. So alpha is going to belong to the set defined by the nodes of the entire mesh minus IH. Yeah? And then I have phi alpha U alpha. And again, all of these degrees of freedom are just scalars, and this is what we use to define the space. So I really liked this expression, because in a way you keep what you had before, the standard finite element, which is linear, and then you're adding something to it. In this case, we're adding nonlinear functions. So you could already see that the P version of the finite element method is in a way an enriched formulation, because we're adding something else to the standard finite element space to help us improve the accuracy of the approximation. Yeah. So with that in mind, I think we are ready to formulate what the generalized finite element space is. And that's it. I mean, once we get to understand this, then the rest is just subtleties, how to implement this or how to do that, to split elements, to create integration elements. But the framework is pretty much the same. Okay. So let's get to define our GFEM space. Let's bring this here. We're gonna call this space as E, and it's going to be defined as the functions UH such that UH is equal to, and we're gonna keep the same notation as before. You have alpha belonging to the index set IH, and then we're gonna add another sum here that goes from I equals to 1 to some value m alpha, which denotes the number of enrichment functions that we will use. And then we have some u alpha j phi alpha j. And this equation can be rewritten as well, let me just copy this back. Phi alpha, and then we have and then of course again we have, since this is a space, this u tilde alpha j, these are now going to be our degrees of freedom, right? But just to complete, let's say that this guy here is called our, let's make it the other way, enriched doves. This function phi, notice that I am using a different form of phi here. It's called the generalized enrichment function. Okay? And as you can see, if you compare these two, the way I wrote these two equations, phi is basically the multiplication of an enrichment function, which is this guy here, yeah, with the finite element shape function of your partition of unity, which is what we discussed earlier, right? If we take any function we want that has some interesting behavior, right, and then we multiply that function by our partition of unity shape function, right? This product is what I called phi, this other form of phi, and we call that the generalized enrichment function.
But at the beginning you said that that function just scales the former function, right?
Mm-hmm.
Just, okay.
Yeah, so this is our enrichment space.
So also that enriched function holds the Kronecker delta property.
Which one, the enrichment function?
The enriched function.
No, the enriched function does not hold the Kronecker delta property. No, no, no. That is anything you want. This L function, and basically the point of this course is to look into what type of enrichment functions you can use to solve different problems, right? So that L could be anything you want. Could be an exponential function, could be a sine function, could be discontinuous function, the Heaviside function, could be anything you want. The idea here is that this is basically my enriched space. By the way, this is still not the entire formulation. Okay, we're gonna get there. This is just the enriched space, and you can see that it's defined by just the product of enrichment functions with those of the partition of unity shape functions.
Are you going to visualize it conceptually? Or
In the book you have that.
oh, okay.
Yeah, Have you noticed? Have you who has seen the Nota Bene already, the book? Yeah. Okay. So there you have a few examples. Yeah, because it's very hard to do this multiplication, you know, like in class, but it's all there. Okay. So this enriched space is what we're going to use to improve our standard FEM space. Right? So you can immediately see that I have now an enriched space, but this is not still the formulation that I want to use. So I'm going to use that space to augment or to enrich my what space?
Could you repeat your question?
So the question is, I have an enriched space, right, that is using these enrichment functions that could represent anything we know about the problem, right, some a priori knowledge about the problem. Now, am I just going to use that space, or I'm going to use it to enhance something else? Yeah, and what is that something else? Yeah, and that is the whole thing. That is the whole GFEM. So you take your standard finite element space, and then you add another space. You are enhancing that standard finite element space by adding some functions with a nice behavior. That's all there is to it. Okay. So this space then is used to hierarchically augment the finite element method approximation so that the GFEM space is, now we are ready to put our GFEM space, because before we just had the enriched space. So now our SGFEM is just taking SH plus SE. Yeah, that's all there is to it.
So we don't consider p-FEM anymore? Or
Oh,
again?
we can consider p-FEM. And in fact, that is the work of Yi here. she's using that as our let's say not enriched space, and then she's basically building on top of p-FEM, adding enrichments. So that's her master assignment, and it's going well, right? Okay, so now we have our space. So let's write how does the function looks like if we're just adding two things. Yeah. And as you can see here, actually, let me just write it so that this is perhaps the most important equation that you will see in this course. That's it. This is the method. This is the GFEM, right? So here we have our standard FEM that is augmented or enriched by this enriched space. So we have this extra component. And in this extra component, we have these ones. We call them enrichment functions, right? Notice that I use different symbols for the standard degrees of freedom and for enriched degrees of freedom. So these are my enriched DOFs. These here are my standard DOFs, and these ones are my standard shape functions, which is the same as this one. And again, this product of the standard shape function with the enrichment function is what is doing the localization of this. Yeah? You have a question?
Yes. So similar to p-FEM, the enriched DOFs don't have any physical meaning?
Correct. Yeah, unless you do something particular, those enriched degrees of freedom normally do not have any physical meaning, right? In the discontinuity-enriched FEM, which is the method that we put forward for modeling fracture, we did assign a physical meaning to the enriched degree of freedom to represent the jump, the jump in the displacement. But normally in GFEM, those enriched degrees of freedom do not have a physical meaning. Yeah? So let's see. Two important things regarding this equation, and then we take a break. Because this whole formulation is based on, again, the reproducing condition. The fact that we can pretty much add any function that we want and really represent that behavior. That is called the reproducing condition, right? And this is because of the partition of unity. So if we take, well, let's write this down, reproducing condition. If we take, notice my change, I'm now using the phi to represent the generalized enrichment function, which is a product of the two, which is basically phi alpha x multiplied by, right? Since that enrichment function is basically the same, I can basically take out that and because of the partition of unity, I know that this is equal to 1 and this is equal to Li of x. Yeah, so this basically means that if I add a function, let's say epsilon to the power of x, if I multiply that function with the partition of unity, I can still reproduce e to the power of x because of this partition of unity property. That is the reproducing condition. And the other thing that you can think of is that you are actually, by doing this type of formulation, you are pasting local types of approximation together, right? We looked at, okay, we saw a cloud and we said, well, what if we multiply the shape function of that node by some function? Well, the behavior is localized in that cloud. Well, the cloud next to it could have a different behavior, could have another function, right? And so you can think of this method as really pasting together different approximations in different clouds of your domain. Yeah? Yeah, this is another way to write that equation. And here, again, we have our partition of unity. This is normally the way it's written. You will find that in papers. And this is the local approximation of U. So again, I'm going to repeat what I said a minute ago. If you take different clouds, every cloud can have its own behavior. So this framework allows you to basically think of in terms of getting all these different patches, the behavior of all these different patches, and combine them together. Now, of course, you may argue, well, what about that element that belongs to two contiguous patches or clouds that has different functions in it, right? So that element belongs to, let's say, patch 1, but also belongs to patch 2. And if in patch 1 the functionality is for, let's say, a discontinuous enrichment function, and for patch 2 the functionality is for some exponential function, well, indeed, that element is going to have both functionalities. You see that? So far, all of this is a bit abstract, right? But that is as abstract that we're going to get in this course. That's it. Now the idea is, let's explore the method. Let's see what are the type of enrichment functions that we're going to use to solve different problems. Some enrichment functions work, some do not work, why they do not work, how to make them work, right? And that is basically the objective of this course. Any questions up to this point before we take a quick break? Yeah.
How can we choose the enrichment functions?
That is a very good question. How do we enrich how do we choose the enrichment function? Well, it really depends on your problem. If you know that, let's say, in your domain, at a particular location, there is a singularity, then you would choose a singular enrichment close to that location. Now, if the enrichment that you provide to the approximation is not useful, what's going to happen to the associated degree of freedom? Yeah, Galerkin, to the rescue, is going to tell us, well, that enrichment that you added is really not that important for our problem. So by minimizing the error with respect to the space of function that we're using, right, it's basically going to get rid of that enrichment because it's really not used. Yeah, and that has happened to us in the past. Like let's say we add an enrichment somewhere and we say, well, let's I'm sure this is going to work, and I'm convinced it's going to work, and then I get a zero coefficient, and I'm like, what happened? And then I realized, yeah, it's really not doing what I wanted it to do. Yeah, so this is important. You're adding a priori information about your problem to improve the approximation. Now that approximation could be anything, could be any function you can think of. And there is actually very cool work by Armando Duarte, right? He's one of the pioneers of the method. He's the one we're writing this book together with. And he came up with a way of creating these enrichment functions numerically. So forget about a function. It's not an exponential function. But imagine that you're actually solving a problem numerically, and that becomes your enrichment function to enrich something else. That's very cool, okay? Because you can think of, let's say, solving multi-scale problems where you are enriching your macroscopic scale with some information that you obtain at a lower scale. That is cool stuff. Anyways, let's take a quick break, and then we continue with the class.